Okay, so it's bang on 5 o'clock. Let's get started. Good afternoon, grade 11s and grade 12s. It's really nice to have you here with us again in our holiday lesson. When we were together on Tuesday, we had spoken about problem-solving strategies in Euclidean geometry. And if you all recall, the reason that we had decided to work with Euclidean geometry is because this is a section that both grade 11s and grade 12s have done. And of course, as you guys well know by now, everything that you learned in grade 11 is really, really important for matric. I don't think I mentioned this the last time, but did you know that in your final papers, well, certainly in your trials paper and your final paper, which is going to be out of 150 marks, the Euclidean geometry section is out of 50. And 25 of those marks are grade 11 circle geometry, and the other 25 are the matric geometry theorems. So grade 11 circle geometry is very, very, very important. Okay, it will definitely be seen as the easier questions in grade 12, but sometimes they can make them really difficult as well, as you're going to see today. Okay, so let's get started. We were talking the last time about steps that we can use to help us solve problems. So let's just run through those again, although we should be familiar with them. All right, so the first thing that we wanted to highlight, or that I wanted to highlight to you, was how important it is to read the problem first. Okay, you've got to read the information that has been given to you. Remember to highlight things that are important, keywords. And if there's any information that has been given to you in the paragraph above the question and is not on the diagram, make sure that you write it onto the diagram before you start proceeding. The next thing, if you recall, was to use keywords to make connections between theorems, okay, that you might have to use for this particular problem. So keywords like the word tangent or center or diameter, things like that. All right, and then we would need to go and link those to the theorems that we know. The other thing that I want to stress before we get started, once you've read the questions, ask yourself, what does this mean? I think that's a really, really important strategy in maths, okay? And not just in Euclidean geometry, but in all sections, we can ask ourselves when we've been given information, what does this mean? How do I interpret this? How do I understand it? And then that often gives us a starting point as to how to use this information. All right, so we're going to look at what they're asking us to try and prove and see if there are any lines or angles that these things are equal to. We're looking for connections between the known and the unknown. Often in geometry, we need to work backwards. We need to start the finding. Sorry, listen to me. We need to find a starting point, and that can often be quite tricky, especially with problem solving. In problem solving, the whole idea is that we don't know where to start. So we're going to talk about that a little bit as well. And then again, remember, you've got to write your answer in a logical, stepwise way, and you've got to provide reasons. Okay, so like I had said the last time, when you write down a statement, a mathematical statement, normally in the form of an equation, the very next thing that you do is you go and you write your reason next to it, and then you do your solution below. Okay, is everybody feeling good? Does that make sense? We're all fine. We can jump into our first question. Now, this comes out of a matric paper. I just want to bring your attention to something first. Can you see how many marks it's out of? 7. Okay, so that's a lot of marks. This is generally the sort of question that we would look at and we would go, "Oy, okay, this is going to be difficult." All right, let's go and do as I have suggested. Let's read the information first. Okay, so in the diagram, O is the center of the circle. So straight away, there's a keyword there. Anza, what keyword in the first sentence do you think is important?
Tangent.
Tangent. In the first, it is. Tangent is an important word, but in the first sentence, before we get to the word tangent, what do you think is important? Let's have a look what's going on in the, yes, there we go. Okay, so a lot of you are saying center. Cool, absolutely, guys. Okay, so the center of the circle. All right, so the minute we see the word center, and again, you can put this into the chat for me, what theorem do you link that to? What's the first thing that comes into your head? Pop it into the chat, guys. What's the first thing that you think of when you read the word center? Fair enough. Okay, there will be a radius. Sure. All right, line from Kyra, there we go. Diameter, fair enough. I would also think that. Chord, I don't know if I would necessarily think chord, but I would definitely think diameter. I would definitely think radius. I would definitely think angle at center is twice angle at circumference. And a few of you have said that. That's amazing. Well done. Awesome. All right, so let's make a note of that. All right, when we see the word center, one of the things that we think about is angle at center is 2 times angle at circumference. Okay, and that's a really long reason, isn't it? Okay, reading on, we can see that ST is a tangent to the circle at T. So now in this sentence, what is the key word? What's important for us here? Let's use a different color. Let's go with yellow. Again, you can pop that into the chat if you want to. What's the key word in this sentence, Matrix and grade 11s? Okay, Atule, yes. Yes, Tabile. Yes, Njabulo. Yes, Mamelo. Perfect. The word tangent. Okay, so now I'm going to call on someone. Punita, if you're feeling brave, you're welcome to unmute. All right. When you read the word tangent, what do you think of, Punita? Theorem 7, 8, and 9. Okay, fine, fair enough. Fair enough. But what is theorem 7? What is theorem 8? What's theorem 9? Can you type it quickly for me, Punita? There we go. Okay, everybody's saying tan chord theorem. Okay, so that's what you know is theorem number 7. Okay. Do you know that it's actually not called theorem 7? I mean, it is the 7th theorem that you learn, but it doesn't actually have a name, theorem 7. But it doesn't matter. Yeah, tan chord theorem, that's exactly it. All right, so we start thinking about tan chord theorem. The other things that I suppose we could also think about is radius perpendicular to tangent. We could also think about tangents from the same point as well, but that's not going to be in this particular diagram. But great, at least now we're linking the keywords to the theorems. Reading on, they tell us that T, M, and P are points on the circle such that Tm equals MP. And we go and we have a look at the diagram and we can see that they've marked that all for us. So we don't need to do that. And we're happy about that. Then they tell us that OT, OP, and TP are drawn. And the last thing that they tell us is that O1 is equal to X. Undi Balele, I see you've asked a question. You've raised your hand. Do you want to ask a question before we get started? You can unmute if you want to. Undi Balele, I hope I'm pronouncing your name correctly. Do you want to ask a question? No? Okay, well, I'm gonna carry on. If you do want to speak, then you are more than welcome to unmute and ask a question. All right, guys, so now we have a look at this diagram and we can identify the tangent. There it is, ST over here. So here's our tangent. Okay, there's O, the center of our circle. We can also see they've given us angle O1, which they've called X. And then we've got this four-sided shape over here, a diamond shape. Two sides are equal to one another. And then when we go down here, we read, prove with reasons that STM is 1/4 X. All right, so now the next thing that we want to do is go to the diagram and identify what STM is. All right, so you can pop this into the chat. What other name could I call STM in the context of this diagram? What angle are they referring to?
T1.
T1, quite right, Anza. Okay, and what can you see about angle T1? Is there anything that you notice about it in particular? Rory, what do you notice about angle T1? If you want to unmute, Rory. Rory, don't be shy. What do you notice about angle T1? You don't feel like talking today, Rory. Okay. All right, let's have a look in the chat and see what's going on there. Roro-san, you saying, ma'am, what's wrong? I can't hear. Okay. Undi Balele, I'll ask one of the TAs to see if they can sort you out. Roro-san, when you say which one, we're talking about angle T1. What do you notice about angle T1? What's important about that angle? Okay, some of you are saying T1 equals P1. Good, Masejo. Good, Thelma. Yes, equal to P1. 100%. Okay, so you guys are on the right track here. T1 equals P1. Good. So straight away, you can see that it's the angle between the tangent and the chord, and then it's going to be equal to the angle in the alternate segment. Now that you know that, all right, now that you know that angle T1 is equal to angle P1, is there another angle that T1 and P1 are equal to? Or are they only equal to one another?
It's equal to T2.
It's also equal to T2. What's the reason for that? I'm sorry, I didn't see who unmuted there. Who was talking? It
Was me, ma'am.
It was you, Anza. Okay, go for it, Anza. So it's equal to T2 as well. What's the reason for that, Anza?
Equal sides. Opposite
Okay, so
angles of an isosceles triangle.
Okay, but Anza, if you say that in your exams, you're not going to get any marks. Okay, I know it's such a difficult thing for us to remember. I know the boys I teach also struggle to remember it as well. It's angles, opposite, equal, sides. Back in the day, like when I was at high school, we used to say base angles of an isosceles triangle, but the Department of Education no longer accept that as a reason, unfortunately. So it's going to be angles, opposite, equal sides. That's it. Great. So a lot of you have put that into the chat, which is nice. Michelle, ma'am, could you also say equal angles, equal sides? No, Michelle, you actually can't. It's got to be angles, opposite, equal sides. They're quite funny about that. What you might also be thinking about is where you've got equal chords, equal angles, which is part of angles in the same segment. But no, you can't say it in any other way. It's got to be angles, opposite, equal sides. And then, of course, it's got a converse, not that we call it a converse, but the opposite of that is sides, opposite, equal, angles as well. Okay, but yeah, angles, opposite, equal, sides, if that's what we've been given. All right, nice. So now we've been able to identify a couple of things that T1 is equal to. All right, and that T2 is equal to, and that P1 is equal to. They're all equal to one another in this case. But the question has asked us to prove with reasons that STM is a quarter of X. So we've got to find a way of being able to relate X to these angles that we've highlighted in yellow. So now, instead of me telling you, I want to hear from you. What do you think? Where do you think we need to start? This is non-routine. We don't have a clear starting point. Where do you think we need to start with this? What does your gut say to you? Yes. Who's talking?
Could you please,
Redo. Yes, Redo.
Could you please repeat your question? I didn't hear it.
Sure. So Redo, what I was saying is you need to look for a starting point. Okay, we've got to start this off in some way, because what they've asked us to do is that they've asked us to show that angle T1 is a quarter of the size of X. So I'm asking you, where do you think you should start? So is that clear?
Yes, ma'am. Thank you.
Okay. All right, no problem. All right, so there's a couple of suggestions in the chat, guys. Someone has said that M is equal to half X. Okay. T1, fine. Kakleho also says M is equal to half X. Sihawu says find M. And then another suggestion, M is half of X. Why is M half of X? So M is equal to half X, angle at center is twice angle at circumference. I'm so glad that you are saying this, because you are wrong. Okay, you've got the right idea, but you're saying the wrong thing. So the trap, there we go, Prosper. There we go. Now, I want to show you guys something. Before I say anything else, I just want to show you something right now. I haven't done this before, so just give me a second. I want to show you this. All right, so the TAs can let me know if I'm doing this right. Can you see that? Can everybody see the arrow on the screen? And it says the angle at the center is double the angle at the circumference. Can we all see that? You can see it. Cool beans. All right, now, I want you to have a look at this, right? This is a program called GeoGebra, and it's really awesome for circle geometry. So here we can see the angle at the center, which is 137 degrees, is twice the angle at the circumference. This one happens to be 69. And what's really cool about this program is that I can move it like this. So you can see that I can make the angle at the center smaller, and then the angle at the circumference also becomes smaller. It's always going to be half. But I can also, so in its current format, we've got an arrow shape, all right? But we know that angle at center is twice angle at circumference. It doesn't always come as an arrow. I can also do this. Look there, can you see how it's crossing over one another? Okay, so we've seen that before as well. So sometimes it crosses over. And again, I can change the size of the angle at the center, and then the angle at the circumference is always going to be half that size. All right, so I can move this around. Okay, if I wanted to, I could move it around to that side as well. Now check out this. Okay, so you've got that, you've got the crossover, you've got the arrowhead, and now look at this, guys. I think this is amazing. Now I'm going to move my arms up here. Not moving that. Here. Look. Why do you think that I'm showing you this?
Oh.
Are we starting to put things together now, maybe? Right,
Yes.
there is this diamond shape thing, okay, this diamond shaped quadrilateral on the inside of our circle. Tobile, is it a cyclic quad? What do you think?
Pardon me?
Is it a cyclic quad?
Yes.
Okay, all right, so I'm glad you said that because you're wrong. All right, it's not a cyclic quad. Why is it not cyclic? So there are a few of you that are saying no. Suzanne, why is it not cyclic?
Well, ma'am, because not all four sides are touching into the circle.
Absolutely, not all 4 points are on the circle. So 3 of the points are in the circle, but the other point is at the center. All right, so it's not a cyclic quad. All right, this is angle at center is twice angle at circumference. So now that we've had a look at this and we can see, right, over here, we've got these arms that come out. It's the angle on the outside of that, the reflex angle, that's going to be equal to twice the angle at the circumference. So hopefully when you look at this and you can see how it forms the arrow, how it forms this crossing over thing. I don't know what we call that. Like, it's not a bow tie. And then very importantly, if we raise these points further up, we can still see that the angle at the center, the reflex angle at the center, is still twice the angle at the circumference. So now that I've showed you this, all right, let's go back. Hang on one moment. Where were we? That's it. I want to go back here. All right. And now, hopefully, we can see in this diagram what I've just been trying to show you in GeoGebra. All right. So now there are some things in the chat. So Anza, you're saying M is 360 minus X. Close, but not true. Bushuluvava, you have said M is equal to half 360 minus X. There we go. We're starting to get closer. Dalen, you've raised your hand. What did you want to ask? You saw your mistake. Okay, Andre. Yes, go for it, Dalen. Sorry.
Is MTP not the isosceles angle?
MTP is an isosceles triangle. You're quite right, Dalen, it is. But you're not allowed to say, you're not allowed to use the words isosceles triangle as a reason.
Okay, Miss.
Okay, that's
Thank you.
not allowed anymore. So if you want to say that P1 equals T2, we call it now, the new way of saying it is angles opposite equal sides. Okay, so M is a half of X. No, Lorata, M is not half of X. Somebody did say something earlier which was spot on. I'm just trying to go back and see who it was here. Right. Remember, the angle at the center is twice the angle at the circumference, right? So if O1 is X, how big is O2? Not X minus 360, the other way around.
Ma'am, it will be equal to O2 plus O1 will be equal to 360. So it will be 360 minus X, which the reason would be angles around a point.
Absolutely. Good. Well done. So it's going to be 360 minus X. Yes, Tokozile, now you're thinking. Now you're thinking. That's great. I love what you've just put into the chat for us. Okay, so the angle at the center, the reflex angle at the center, the one in purple, angle O2, is going to be twice the size of the angle at the circumference, which is going to be M. Right, so now I have to write how big M is in terms of X. So now I'm not going to do that. I want someone to tell me what M is in terms of X. How big is M?
Can you say M is 2X?
Unfortunately not. Remember, we're dividing by 2. Okay, so what you've got to do, I love your suggestion, but what you've got to do is you've got to take 360 minus X, and you have to divide that by
2.
2.
So is it going to be 180 minus X over 2? Or is it just 100?
No, 100%. Okay, so, or you could write it as half X. Perfect. So Bushule, you've raised your hand again. Do you want to ask a question? Yeah, what Eric's putting in the chat is perfect. There should be brackets there. No, you don't want to ask a question. All right. So I just want to find out if everybody is happy with the idea that the angle at M is half the angle of O2 because of angle at center is twice angle at circumference. And if we take 360 and minus X and we divide it by 2, we would say 360 divided by 2, which is 180. And then obviously negative 1X divided by 2 would give us minus half X. Bushele, you've raised your hand again. What's your question?
Ma'am, couldn't you have just said M is equals to 360, half 360 minus X?
Absolutely. So if you want to, you could do this. You would say M is equal to half of 360 minus X. Absolutely. And then in grade 8, do you remember how we expanded brackets in grade 8, where we multiplied the factor on the outside with the first term and the factor on the outside with the second term? So a half times 360 is 360 divided by 2, which gives us 180. And then a half times minus X would give us minus half X. I suppose the other way that we could write that if we wanted to is we could write it as minus X over 2. That would also be acceptable in this case. All right, so there's a couple of people. All right, first of all, before we carry on, I see there's a couple of people that say they don't know what's going on. Where did we get the half? Ma'am, please repeat how we got 180. I just want to see if it's just those people or if there are a lot of people that don't understand. So can you put in the chat this very specifically, okay? Do you understand why M is equal to 180 degrees minus half X? Thumbs up for yes, thumbs down for no. Into the chat, please. We are specifically talking about understanding that M is 180 minus half X. Okay, thumbs up for yes, thumbs down for no. Okay, thanks for your responses, everybody. I can see, I would say probably the majority of you do know, but there are certainly quite a few people that don't understand. Okay, so what I'm going to do then, that's fine. Thank you very much for your responses. Let me just explain it again. So those of you that do understand, my apologies. I just don't want to proceed if there are still quite a lot of people that don't understand this. Okay, so those of you that are not understanding what I'm saying, I'm just going to rub this out. And then we'll talk about it one more time. Okay, so angle O2 is the angle at the center. Can you see this arm over here, line OP and line OT are radii? Okay. And they have been lifted. So if it was in an arrow configuration, P and T would be further down the circle, but they've been lifted up. Okay, so it is the angle on this side over here that is the angle at the center, angle O2, which is a reflex angle, and it subtends angle M at the circle. So angle O2 is twice the size of M. Angle at center equals 2 times angle at circumference. Okay. Angle O2 can be obtained by subtracting x from 360. So it is equal to 360 minus x. So if 360 minus x, which is O2, is equal to 2 of m, then in order to get m on its own, we would have to divide both sides by 2. Okay, so I'm going to divide by 2 on the right-hand side of my equation. And that means I must divide by 2 on the left-hand side as well. So 2 divided by 2 means I've got m on its own. So 360 minus x divided by 2, you can write this as this. So it's 360 over 2 minus x over 2. 360 divided by 2 is 180. And x divided by 2 is x divided by 2, or 1/2 of x. Does that, for, ma'am, what would the reason be for O2 to be 360 minus x? That would be angles around a point. Angles around a point. Sorry, I'm squashing it up a little bit here. I hope you guys can see that. Okay, so O2 is 360 minus x because of a revolution, or you can say angles around a point. Okay, Roro-san? All right, so now the people that had a thumbs down, how do you feel now about we're not trying to get 2m, we're just trying to get m on its own, a p-way. Right, we want to get m on its own. Right, we don't want 2m, we want m on its own. What do you see, David? Cool, Jamila, I'm glad. Thanks, Relebohile. David, what do you see? Oh, you mean you see now, you understand. Okay, all right, much better. Cool. All right, so now we're going to continue. Right, now that we know how big m is in terms of x, we need to try and relate that back to angle T1. Now we know that angle T2 and angle P1 are equal to one another. That makes TMP an isosceles triangle. Right? So now we want to work inside that triangle and try and get an expression for P1, because P1 and T1 are equal to one another because of tan-chord theorem. This is us now trying to work backwards. So has anybody got a suggestion as to what we can write? Cool and Paul, I'm glad. I don't think I said that right, but anyway, I'm glad you feel a little bit better. How am I going to relate P1 and M and T2 to angles of a triangle? What should we write there? Anyone got a suggestion?
Ma'am, can I use sum of angles in a triangle?
Absolutely, Cassandra. Absolutely. So in other words, what we have is angle M plus angle P1 plus angle T2 that adds up to 180 degrees because of angle sum and triangle. Perfect. Right. Now, P1 is equal to T1 because of tan chord theorem. So does it make sense if I then say that angle M, actually, before we do that, let's do this, sorry. But P1 equals T2. Can anyone remember what the reason is again? Not allowed to use the word isosceles. Could pop it into the chat. Let's have a look.
Angles opposite equal sides.
That's it. Lovely. Angles opposite equal sides. Angles opposite equal sides. So then it makes sense, I hope, if I say that M plus 2 of P1 will give me 180 degrees. Yes, so angles opposite equal sides. Does that make sense to you, grade 11s and matrics? That M plus 2 of P1 would be 180. And give me a thumbs up if that makes sense in the chat. Thanks, Thelma. Lekker. Okay. Thanks, guys. Sihawo doesn't make sense. Okay, that's because Sihawo is because P1 and T2 are equal to one another. So if I have 2 of P1, I have P1 plus T2. Okay, I'm just rewriting that in a different way. Okay, so now it's time to substitute. We know that M is 180 plus half x. Sorry, minus half x, beg your pardon. Would have been a bit of a disaster, wouldn't it? Okay, so M, I'm now substituting. M is 180 minus half x plus 2 of P1 gives us 180. Now I want to solve for 2 of angle P1, right? Which means that I'm going to take the 180 and the minus half x over to the other side. So 2 of P1 is going to be equal to, Chantal. What is it going to be equal to, Chantal?
$180 minus half x.
But actually, when the minus goes over to the other side, what's going to happen to its sign?
It changes.
It changes. So is it going to be minus half x on the other side as well?
No, ma'am.
No, it's not.
Okay,
so if we leave this on the left-hand side of the equation, and we take the 180 and the minus half x over to the other side, what's going to be left on the right-hand side all by itself? Yes, Kanyasile. Yes, Cassandra, quite right. Yes, who else said that? I want to have a look here. Someone else. Yes, half x, good. Yes, you guys have got it. All right, so now I made a mark on the page here that I didn't mean to. Let's just get rid of that. Good. All right, so we have 2 of px is equal to half x. And now if I want to get P1 on its own, because remember P1 is equal to T1. 1 of P1 is equal to 1 of T1. And I want to solve for T1. Right? What am I going to do to both sides of my equation now?
Divided by 2.
Divide by 2, absolutely. All right, divide both sides by 2. So Thokozile, when I say a half x divided by 2, what does that give me?
Quarter.
I beg your pardon? There we go. Kanisile, a corner, a tule, quite right. It's going to give me 1/4 of x.
It gives me 1/4.
It certainly does give me 1/4. Okay, and Boitshepo, you can do this part for us, please. How are we now going to relate P1 back to T1 or STM? What's the last step in solving this problem? What would we write?
Ma'am, don't we say that T1 will also be a quarter x because of Ten-Cot theorem?
Okay, but T2, it's not because of T2, okay? So T1 and P1 are equal to one another because of Ten-Cot theorem, right? The fact that T2 and T1 are equal to one another at this point in the question doesn't actually have any bearing on the answer. Okay, what's important now, and I see some of you are saying that in the chat, is Ten-Cot theorem between P1 and T1. Okay, Boitshepo, do you want to give it a try? What do you think the last thing I should write is?
I think we should write, ma'am, I'm not sure because of T3, because I'm not sure about that, if it occurs with T1 and T2.
Okay, so T3 is not important to us in this case at all. It's got no bearing on our answer. We're right at the very, very, very last step. Just hang on, there's just something in the chat. Rory-san, yes, so it's the 3 dots means therefore, quite right. Prosper, you've said T1 equals 1/4 x. Absolutely, that's right. P1 equals STM, Menentle, good. Mamelo, you've said P1 equals T1. Ten-Cot theorem, you're all correct. Okay, all correct. We're right at the very last point. So now we can conclude that STM or T1 is also equal to 1/4 x, and our reason there was Ten-Cot theorem. Okay, so Boitshepo, can you see it was actually a little bit easier than you perhaps thought? Okay, you were just right at the end. You just needed to make the conclusion. We have proved it. All right. How do you feel?
I feel like I didn't see that because I thought that everything for T1, 2, and 3 had to do with the angle of STMs equals to
Yes.
1/4 x. But then now I
Yes.
realize that now it's clear.
Yeah, okay, good. Cool, I'm so pleased. And the rest of you, how do you feel about this? Oh, thanks, Riyadh. I appreciate that. I'm glad that was a good explanation. And I hope that you can see how, you know, the way that I've described how you should try and look at the problem, those steps, how it's come into each way that we've done that. Cool, it's nice to see all the thumbs ups. Well done, guys. That's great. Thanks for all the interaction. Cool. Well, you see, now maybe you've got the confidence to try these sorts of questions, whereas before maybe you would have just said no, Thokozile or Cassandra. Nice. Okay, so we've got 20 minutes left. Thanks, Neo. Thanks, Nolatundo. Yeah, that's true, Miso. All right, let's go and have a look at the next question that I've got prepared for you. This is quite a difficult one, but I don't know with time whether we're going to be able to do everything, but we'll try and do as much as we possibly can. All right, now, no one have a heart attack when you see this. It is a confusing diagram, but I'm doing this on purpose because we said that we were going to focus on problem solving today. All right, so yeah, ignore the little pictures of me. If those are distracting, I can always move them out the way. Again, first starting point is to always read the information that has been given. Okay, so it says in the diagram below, 2 circles touch each other externally at point P. I will move this into the middle of the thing so we can look at it more closely. It says that QPR is a common tangent to both circles at P. All right, so point P is this one in the center over here, right? So this point in the center. What do you notice before we even get started? When we've got all these straight lines crossing over one another, what sort of angles are being created at P, grade 11s and grade 12s?
Vertically opposite.
Exactly. Who said that?
Ranewa.
Ranewa, beautiful. Love it. Okay. 100%. Okay, we've got a lot of vertically opposite angles here. So this is going to be important for us as well. Okay. Before we do that though, let's just finish off and go and read this. QPR is a common tangent to both circles at P. So QPR is this line over here. Oh, let me try and make it a little bit fatter a minute. It's this line over here. I don't want to put too much on the diagram because it will start to become confusing because there is so much. No, David, A, B, C, D, if that's what you mean, is not a cyclic quad. And the reason it's not cyclic, David, is because?
Ma'am, is it because it occurs in two circles?
Absolutely, absolutely, Cassandra. So you can't have a cyclic quad. You can't assume that it's cyclic if it's got its points on two different circles. If it's got its all 4 points on one circle, on the same circle, then it's fine, but not if it's two different circles. I mean, we could maybe prove that it's cyclic, but I don't think that's one of the questions that they've asked us. Yes, Kunani, this is the sort of question that you will get at the end of grade 12 or grade 11 in circle geometry. All right, so that's why I wanted to do this one today. All right, let me move on. Again, we see the word tangent. So as soon as we see the word tangent, we start thinking about all our theorems associated with tangents. Okay, so tan chord theorem, tangents from the same point, and radius perpendicular to tangent. Then we can also see that they have told us that EDRC is also a tangent to the circle. So EDRC is down here. Let's color that in a different color. Here's EDRC. Right, and it's also a tangent to the smaller circle, but not to the larger circle. All right, and we can see here that angle C1 that they've called Y would be the angle between the tangent and the chord. So things being equal, if angle C1 is Y and it's the angle between the tangent and the chord, what other angle inside circle BPCF is also equal to Y, incidentally?
Angle
yes,
T.
Masejo. Can you see which one?
Angle T.
Angle?
T.
Angle P.
T.
Angle B2. Angle B2 will also be equal to Y. So if you put your fingers at C, fingers at C and at P, all right, because CP is your chord, then you're going to follow P and C to the circle. It's going to go to B2. Can you see that, everybody? A corner, can you see that?
No, ma'am, please repeat.
All right, so what I'm saying here, all right, is that because this line here, ERC, is a tangent to the circle, the one that I'm coloring in green, that's the tangent. So the angle between the tangent and the chord is CP, and it subtends the angle at the circle, which is B2. All right, so I'm going to rub this out, but there's your chord. Here's Y, which is the angle between the tangent and the chord, and it subtends B2 at the circle. Can you see that now? So that's why B2 is also equal to Y in this case.
Yes, ma'am.
All right. Okay, so there's a lot going on in this diagram. Let's just go up and go and read the other information. Then they have told us that RCA is equal to Y, DAC is equal to X, and they have told us that AD is parallel to BC. The first question that they want us to answer is name with reasons 4 other angles that are equal to x in this case. All right, so the first thing that we want to do is we want to go and identify x on the diagram and then start making connections between the known and the unknown. Okay, so Bushule, you've raised your hand again. What's the question?
No, ma'am, it's not a question I was going to answer.
Oh, were you? Okay, beg your pardon. Okay, so now that I've got you, what angle is x also equal to?
A C2 alternate angle.
Okay, let's have it up. C2. Why is it equal to C2? What's the reason?
Alternate angles, ma'am.
Lovely, good job. Okay, so because of alternate angles, because of parallel lines, very nice. Okay, so I'm going to pop that onto the diagram. Then I see there's other people with their hands up. Who else had a, does anybody else see another angle besides C2? Yes, can you see there?
Ma'am, x P1 will also be equals to x because of Ten-Caught theorem.
P1.
Yes, ma'am.
Okay, good, nice spot, well done. So this angle over here. In the chat, I can see that Suzanne has said angle E. And so has Thelma. That's really good as well. So if you look at this big circle, right, angle E is also equal to x.
Yes, ma'am.
Because of angles in the same segment. Lovely, you guys are seeing all of this. Prosper, you say that B equals D. Okay. What exactly equals D? So B, at B, there's 2 angles. There's B1 and B2. At D, there are 3 angles, D1, D2, D3. So you've got to be specific. Okay, Madibani, you say that P5 is also equal to X. All right, why is P5 equal to X, Madibani? Pardon? Okay, remember in the beginning, we said then straight lines exactly, Ovio, because of vertically opposite angles. Also, angle P5 is going to be the angle between the tangent and the chord in this case being BP, and that subtends C2 at the circle. So we could either use vertically opposite angles, or we could also use Ten-Caught theorem if we wanted, if we'd already explained C2 first. D3. Why D3, Tobile? Why D3? Can you see it? Why D3?
No, ma'am. Ma'am, I want to ask a different question.
Oh, do you? Okay, all right.
For P5, can we also say Ten-Caught theorem?
Yes, but you would have to say that if you've done C2 first. Yes, then you certainly could. I'm going to pop all of that onto the page so that we can have all of that in front of us. Kumo, I see you've also got your hand up. Did you want to ask a question? Kumo, did you want to ask a question? Let's just have a look here. Is P6 not also equal to X? Why would P6? I'm not saying that it's not, but I don't see. If you're relating it to angle C2, then no, P6 would not be equal to X, no. Okay, Kumo, you've got the answer. All right, so we've now got angle E is equal to X because of angles in the same segment. We've also got the first one that we were told was that angle C2 is equal to X, so let's put that on the page. C2 is equal to X because of alternate angles, and we mustn't forget to name the parallel lines, otherwise they won't give us the reason. So we need to say that AD is parallel to BC. Okay, and now we can go back and we can say that P1 is equal to X and that's because of tan chord theorem. So in other words, because DAC was equal to X, P1 is equal to X, and now we can say P5 is equal to X, either tan chord theorem, or we could say vertically opposite angles. It doesn't matter. Okay, vertically opposite angles. All right, now can you see that this was out of 7 marks? All right, so there are 8 things here, so a statement and a reason. I think what they would do in this particular case, and I'm obviously not 100% sure about this, but the grade 11 work would be things that would get 2 marks. So there would definitely be a mark on this and a mark on this, and a mark on this and a mark on that. And then presumably the stuff that we've done in grade 8, we would only get 1 mark on. So I think they would obviously give a mark on that, and they would give a mark on that. 1, 2, 3, 4, 5, 6. Probably in this case, maybe this would have been statement reason, because it's vertically opposite, and then the last mark would have been over there. Okay, all right, now we can go on and have a look. Prosper. Sorry, ma'am, doesn't D2 and D3 equal B1 and B2? Why, Prosper? And I'm not 100% sure why this is important at this. Oh, you mean because of, oh, I see what you're doing. Okay, so Prosper, you're working with the alternate angles. All right, that's fine. If we want to say that B2 is equal to D2, they're also equal to Y, that's absolutely fine. I quite agree with you. But let's just go and have a look at the question so that we can see where it is that we're headed. I don't know if we're going to be able to do all of this, but let's at least try and do some. Okay, now they want us to show that EPA is equal to X plus Y. Okay, now that's also a difficult question. It's not obvious where we need to start. Okay, so let's go and first identify where EPA is. All right, so this is where I think your highlighter is such an important tool in geometry. Let's highlight this angle EPA. So E starts at the bottom down over here. So EPA is that angle over there. So in other words, EPA is also P7. Okay, so EPA is also P7. So they're giving us a starting point. They're saying EPA. Now, if you have a look at the diagram, what else is EPA equal to? Can anybody name another angle in the diagram that P7 is equal to?
P3, vertically opposite.
Indeed, it's vertically opposite to P3. I quite agree with you. Sihawu says D1. Good, Sihawu. I like that. D1. Okay, so it's vertically opposite to P3. So let's just write this down on the side. We've got P7, or ETA as they called it. It's equal to P3 because of vertically opposite angles. And it's also equal, P7 is also equal to D1. And the reason for that is angles in the same segment. Okay, so now that we've identified 2 angles that P7 is potentially equal to, is there a way, given the information that we've got, that we could work out how either P3 or D1 are also equal to X plus Y? Are there any other angles that are equal to Y that we could perhaps fill in on this diagram? What else is Y equal to? Is there anything else that needs to go into the diagram? I agree. Vio, D1 angles in the same segment. Agreed. Well, we already know that D2 is equal to Y, don't we? We don't know anything about P3. if we have a look at angle D1, which is one of the suggestions that had been made, can anybody tell me what D1 is equal to? What else does D1 equal in the diagram? Can anybody find a connection between D1 and something else?
Ma'am, is D1 equals to angle C, which is X plus Y because of
because of?
four interior angles.
Not
corresponding.
Yes, Cassandra, that is wonderful. I'm so pleased that you can see that. That's excellent. So Cassandra's actually solved it for us, everybody. Look at this, okay? Here is the transversal lying on its side, okay? Remember, we've been given two pairs of parallel lines. BC, oh, badly drawn by me, is parallel to this line over here. That is line AD. So what Cassandra was saying, everyone, I hope you guys can see this as well, is that we already know that at angle C, this is X plus Y, and it is going to be equal to that angle over there. Good spot, well done. Let's just see what else people are saying in the chat. D1 is equal to A1 plus C1. I don't know why. Exterior angle of a triangle. I don't think so. D1 is equal to A1 plus C1. No, that's not true, Peter, unfortunately. Ndabani, you've said that D1 is equal to C1 plus C2, which it certainly is. Okay, that's it. That's exactly it. All right, so we can see here that D1 is also equal to X plus Y because it is corresponding with angle C1 and C2, and then angle D1 is equal to angle P7 because they are angles in the same segment. So let's write all of that down, okay? Our starting point was identifying what else P7 was equal to. We identified that P7 equaled D1, angles in the same segment. D1 equals C1 plus C2, which is X plus Y because of corresponding angles. So it's actually quite a simple question if you can spot the corresponding angles. Okay, so in 12.2, we are going to say that angle P7 is equal to angle D1 because of angles in the same segment. But D1 is equal to C1 plus C2 because of corresponding angles. And then we mustn't forget to name the parallel lines. The parallel lines are AD parallel to BC in this case. Okay, now we can go ahead and substitute. Right, so therefore angle P7 is equal to X plus Y. All right. Oh, they called it EPA. All right, well, E7 and EPA is the same thing. Let's just call it what they called it. Therefore, EPA is equal to X plus Y. Okay, I see there's a couple of things in the chat. Yes, Roro-san, corresponding angles will only occur when there are parallel lines. Okay, so if you either have to be given that the lines are parallel in order to use corresponding angles, or you would have to prove that the lines are parallel before you could use corresponding angles. Kumo, I don't have any, actually, you know what I do before the lesson ends? You know what you can go and try? Sorry, I'm just kind of like jumping. I'm just going to put this into the video so that you guys can see this, and then you can always go and try these ones on your own. There's this question over here. All right, so you can always come back to this and work out the value of X. That's related to the first question that we had done. So you can try this one. And then the other practice question that you can try is this one over here. I was hoping I'd be able to get this far with you, but I haven't been able to. That's another practice question. Okay, so there you go, Kumo. You can try those ones.
Aye, mama.
Okay, and then if you read in the chat, Eric has also said you can find the quizzes on onto the Watobe website. You can go into your learner account and go to catch up, and then you can go to circle geometry and go and have a look there. Yes, we do lose marks if we don't say parallel lines. Yes, we have to name the parallel lines. Okay, Riyadh. Kumo, pleasure, no problem. Zianda, when you say the full shape, Zianda, do you mean the whole diagram? I hope I've done that. Okay, so yes, unfortunately we need to end off. I'm not going to be able to do that last question. How are you guys feeling now? Is what I've done here, has it made sense to you? You can pop something in the chat, a thumbs up. It's a pleasure, Piwe. It's a pleasure, Riyadh. Riyadh, very happy. Oh, cool. I'm so glad.
Ma'am. Hey, ma'am, it made sense, ma'am. Hey,
Did it really?
Headache. Yes, ma'am, but headache, ma'am.
Yeah, no, definitely headache. Definitely headache. These are the questions at the very end that we try when everything else we know that we've done. Okay, it's the greatest pleasure, everybody. I'm sorry we have to go off. I could sit here all night, but I know we've all got things to do. Okay, good. I'm glad it was worth it, Minnie. Good, Relebochile. I'm glad you learned something today. Okay, well, bye. It's a pleasure. It's an absolute pleasure. Bye, everybody.